Is that better? Yeah, that's better. Hi. Hello, everyone. So, today, we are going to. Well, that is the daily activity for today. So, spoiler alert. We'll talk about that later. Today, we are going to be discussing concurrency. From there, just some notes. Quiz 6 is up to Monday night. Homework 4 is up, and I just want a couple notes. The PDF says homework 5, and it's just because I couldn't find the original Word document to correct it. But those are the only two things that change is I need to rename it to homework 4, and it's not due in April. Obviously, it is due next Tuesday. The homework does not build on homework 3. Homework 4 and 5 will be standalone. They will have nothing to do with homeworks 1 through 3, at least in terms of using the same code base. They won't do that. From there, it is recursion, which is WebCat graded. So this is 50 points. The WebCat is not up, but it will be up basically right after class. I'll need time to set it up, but I will do so. The concurrency portion will be manually graded, and that will be the remaining 50 points, and that includes things like style points, commenting, etc. The recursion part still needs to be commented, so concurrency and style make up the remaining 50 points. So do be aware that those assignments are up. From there, obviously homework 3 is due tonight. I've been seeing a lot of good progress when I've been in office hours and when I have checked on Piazza. It is still due tonight. Not a huge assignment, but it certainly requires homework 2 be in good state before you proceed. But with that, that's pretty much all I have for now. Are there any questions about any of those things? All right. So today we're going to be discussing concurrency. And as we discuss concurrency, the idea of concurrency is that anymore, this does not have one processor. There's a PS4, a PS3, and an Xbox 360 behind me. All of those have multi-core processors. Your laptop probably has multiple cores. Not necessarily, but probably. The standard in programming right now, or I should say in hardware, the standard right now is multiple processors. Or at least multiple cores within a given processor. A single processor, but single processor chip, but multiple processor units. And if I hit on my computer, give me 1 second. If I were to hit on my computer, Control-Alt-Delete, and I pull that up and I do a screen share real quick, which I need to make sure I'm not showing off my tags there. You can see here, this computer has 12 independent processing logical units. It technically only has 6 cores, but each core runs in 2 states. It's kind of hard to explain, but it works, trust me. And each of these processors are currently doing something. I have CPU 0 all the way to CPU 11. Now, all the programs that we have written so far only use one of these. So let's take, for example, I use my sorting examples code from last time. And let's say I run this. I want you to watch that one of the processors will jump. It's not predictable which one it will be, but one of the processors will likely jump when I run this program. So run There it is. You can see the spike right here. Actually, it did swap it among multiple processors, but the key is only one processor was actually being used at a time. If I do a selection sort, it might be a bit more obvious just because that one doesn't work as fast, to say the least. Let's do... Hang on, run. We do run as, run configurations. I don't want to run recursion examples. I want to run sorting examples. Where is that? Oh, well. Let me change it to sorting examples, arguments, selection, 10 million. Okay, let me run this. And if you take a look, you can see it doesn't... You can see this one processor spiked pretty hard. And it does swap, so now it looks like it's bouncing between these two processors. But the key is only one processor is running this program at any given point in time. That's the idea. And that seems fairly wasteful, right? If I have all this processing power, why don't I use that at my disposal to build a program? And Java fairly simply supports doing this. The idea is threads. And so, plug in my whiteboard camera here. And so the idea of threads is that... Hang on. The idea of threads is that as we build our system, we design it such that when we want to perform some tasks, so if this is our main thread of execution, the idea is we branch off some pattern, some thread. This thread is going to execute in parallel. So this is on one processor, this is on another. Now your computer will switch which processor a process is on, but for the sake of simplicity, you can imagine this is two processors and you won't be wrong. And then at some point, this thread does something to the program that affects the main execution thread, whether that is reporting some information back, changing a variable, whatever. And the idea is this thread runs in parallel. They can run at the same time because I have multiple processors. And this is a very important thing. A lot of computing processes will try to use what is called parallelization. That is to say, taking a given process and moving it online. They will try to do that, or excuse me, not online, onto multiple processors. They will try to do that to get efficiency. Now, we get diminishing returns. In a best case scenario, if you have two processes, something takes half as long. You add another processor, it only takes a third as long. So you only gain, instead of 50% efficiency, you only gain 16% on the third processor. Then you go down to 25%, so you're only gaining 8%. The point being, it doesn't solve big O problems. You know, exponential is still exponential. It doesn't matter how many processors you have. It's going to be exponential. It's still going to take a long time. But it can add some benefits. It can also add benefits from a standpoint of program design. So we're going to talk first about how do we create threads, how do we then run those threads, and then how do we get information from those threads. But also we're going to talk about how threads can be kind of dangerous. Now, not to your health and well-being. Don't worry, your computer's not going to turn on you and, you know, try to, I guess, eat your face with the CD drive. Is the best I can think of. Wouldn't be very effective. Don't have to worry about that. Dangerous in terms of it can mess up your data integrity. The idea that your program, at any given point, it's running the operations, but if it runs operations in a certain way, your data can become incorrect. And we'll see an example of that later today. So the basis of a thread, and this is something that Java will use, it is a portion of the program that runs independently. And the Java virtual machine will allocate time pseudo-randomly to all of the threads as well as the main process. And I say pseudo randomly because it's not random. It's not, I'll just throw darts at the board and see what happens. There's a process to it, but that process is so complicated and so inherently unpredictable that it becomes difficult to try to predict it with any certainty, bordering on impossible. Is this like the inline command C++? I will admit to you, I am not familiar with the inline command in C++. It has been 10 years since I have used C++. No, 11. 11 years since I've used C++, and I hated every minute of it. So I've not had a desire to go back. There's reasons I don't like C++. I'm not going to get into them now. So I forgive me that I honestly cannot answer that question. So, threads are created via the runnable interface. The runnable interface is an interface like comparator that we use to make separate classes. So we make a class, an example of runnable, and then we simply need to implement the method run. And here I have such an example, and if you'll notice, on my code today, I have 6 projects that we're going to go through. That's right, 6. It's a lot of code. But that's because I wanted to give you as many examples as I could here. And the thread example 1 is going to be where we start. We're going to iterate through all of these. And I want to start by looking at this runnable. So this is a greeting runnable. It implements runnable. And what it does is first we take in some greeting as a field. We take it in via the constructor, because we can create a constructor when implementing an interface. We didn't with comparator, but we will here with runnable. We'll take in some greeting and store it. And then the run function is simply going to loop iterations number of times, or repetitions numbers of times, so 10. And it's going to pause for 2 full seconds. Actually, this should be 1 second. It will pause for 1 second, but each time it will print the greeting. It will print the time and the greeting, and then pause for 1 second. Actually, for simplicity, let's go ahead and let's remove the pause for the time being. I'll add those things back. So all it's going to do is just loop 10 times and print some greeting. That's all that's going to happen. From there, I don't run in here. Rather, I could run in here. So I could create a runnable. Then from that runnable, I create a thread. And that may seem a bit strange because you may be thinking, why don't we just call r.run? You can do this, but if you do this, this function runs on the same processor as your main program. It's no different than calling a function on the stack. It cannot run in parallel if you do this. So instead, we create our runnable here. Then we create a thread from that runnable. So the thread constructor takes in a runnable object. Then we don't call run, we call thread.start. And thread.start will eventually call run, but it will call run on a separate execution thread. That is to say, so it can run in parallel. And don't worry too much about what this is. I'll talk about that in a second. Why I have that there, it'll make sense soon enough. And when I run this, you'll notice something interesting happens, because I start the thread, and then I say loop over, but if you'll notice, loop over didn't print. Well, why didn't loop over print? Well, loop over didn't print because loop over printed first. The thing about starting a thread is this. Threads, when they start, will run whenever they run. You cannot force them to run. You cannot force them to say, you can't give threads deadlines. Sorry, students, you're not threads. But you cannot give threads deadlines. They will run in their own time. But all that happens when you call t.start is it will call this run method on this instance R of this class. So if I create multiple threads, call this thread T0, and then create a second thread, thread T1, and let's do a second greeting. Make this one S, and then instead of spam, let's say what would be funny? I can't come up with a good meme. It's almost Independence Day, so I'm just gonna go America. There we go. Because America. When I run this, you'll see that the threads, well, hang on. Oh, I didn't pass S. Let me do that. You'll see that when I run them, what am I doing wrong here? Hang on, give me a second. Oh, I never start T1. That's why. You'll see that when I run these, it kind of just bounces between spam and America, and it's not predictable. And this is the first lesson about threads. They are not predictable in terms of when they will run. All you know is that they will eventually run. But the idea of each of these threads is that I take in the constructor some greeting to print, and then I perform repetitions number of times I print that statement. It is not predictable what order those statements will print in. So I didn't get I started the spam thread first. I did not get all of the spams, then all of the Americas. If I run this again, I'll probably get a different order. Yeah, notice this time it just went spam, America, spam, America, spam, America. Which is, I believe, the Twitter strategy of some politicians. The point is, threads are inherently unpredictable, but the base of threads is fairly simple. I had to dial that back like halfway through that joke because I realized I can't be political. But the idea here is we create a class that implements runnable, and we define a run method. And this run method is what gets called when we start the thread. But the key is this is happening on a separate processor. Or at least, if it's on the same processor, it's happening in parallel, in a threaded way. So as a result of this, you'll notice, though, that loop over is always printing before these. Now, the reason for that, it's not always going to happen. It's just because it takes a lot longer to start a thread and actually load it into memory and do it than it does to just print loop over. But if I add in this loop here, this loop is going to calculate the arc cosine of 0.8 a bunch of times. The arc cosine takes a really long time to calculate. So if I run this... Oh, no, that wasn't enough. Let me add a 0. If I run this now, you'll see that now loop over is appearing at the end, and it's just because this loop takes a really long time. Let me remove a 0, change that to a 3. See if... I'm trying to print it in the middle. See if I can time it right. Nope, that was too short. Increase the number. Too short. Too long. There we go. Perfect. Yeah, I probably could have done a binary search, but whatever. That was really more of a fumbling in the dark search. But the point is, notice that I got loop over to spawn in the middle. And it's because, again, these start the threads, but they run in their own time. The main continues in the same main thread of execution. So typically you have a main thread that spawns other threads. But from there, however long this takes, that's where loop over is going to print. So it's inherently unpredictable. Notice this time even America printed first, even though I started the spam thread first. So the point is, these threads are unpredictable in their timing. However, creating them is just step 1, create a runnable class with a run function. Step 2, instantiate the class. Step 3, create a thread from the runnable instance. And then step 4, start. And that's pretty much all you need to do. Is there any questions about this starting point for the threads? And again, all this code is already uploaded. So again, here's my runnable class. Implements runnable. I have a private field that is set by the constructor. These are just constants. And it does run. It prints 10 times. It's going to do the following. Any questions about any of this code so far? And again, this is thread example 1 if you're looking on the class website on the resources I uploaded. Pardon me. Why would you need to use this to write a program? So the reason you would do threading, there's 2 primary reasons. One is efficiency, so you can do multi-processing, because by default, a Java program will only use one processor. And so if you have multiple cores like I do, I can have 12 threads in a program all performing the program's task at the same time to get it faster. That's the first reason. The second reason is there's design reasons for threading that can make building your program more easily. The idea is your program, rather than being synchronous, which is to say you hit run and the program keeps running until it finishes, your program might be asynchronous. An example of this is an instant messaging client. So 2 people are communicating with each other, right? But you have to wait for someone to send the program a message before the program can actually print that. What if I made the program with 13 threads? It would let me even more broadly say it. What if I made the program with 1,000 threads? Well, I can only run 12 concurrently, but the others, I mean, keep in mind, right now on my computer, and this is probably a bad idea to publicly broadcast this, but just to show you what's going on. I mean, right now on my computer, all of these processes are running. Again, this is probably a really bad security idea. All of these processes are currently running. And they're just sharing time. So my program is not always running. My computer is constantly doing multiprocessing. Once you get above 12 threads for a single program with my processor, which has 12 logical processors, once you get above that threshold, you will stop seeing efficiency gains. The program will not get more efficient, but you can still do it if there's design reasons you want that many threads. If you're waiting on asynchronous events, which we're not going to get into in this class. We don't really even have time to do GUI, so kind of just hand wave and trust me on that. The primary reason's efficiency, though. So now, another thing that is worth noting is that there is this thing called threads.sleep. And I want to quickly illustrate what that does. Threads.sleep, or thread.sleep duration, I believe is what I call this. No, delay. This is a function that takes in an integer number of milliseconds. How many threads can we have? How much memory does your computer have? You can have as many threads as you have memory to support. And once you run out of memory, then your program's going to crash. But in theory, you could have as many threads as you wanted. It's just you're only limited by the practical limitations of your computer. Or as Zombocom would say, the only limit is yourself. And nobody here knows what Zombocom is, so don't worry about it. The old internet memes are confusing. Oh, someone here does. Okay. Old internet memes are stranger than you understand. So I'm not going to get too much into the try-catch block because we're going to do this later on in the class. But if you do threads.sleep, you have to have this catch thing. Don't worry too much about it yet. But this is going to tell the thread to wait, in this case, 1,000 milliseconds. How can we know how many processors you have? Depends on your hardware. So look up the computer. If you bought a computer whole, you can typically see what the processor is in the receipt for that. If it's a Windows, I know you can do Control, Alt, Delete, and Task Manager, and then go to Performance. I don't know how to do it on a Mac. If someone does know how to do it on a Mac, go ahead and type it in chat. That would be great. But threads.sleep just says wait X amount of time. So I'm going to wait 1 second between each print, and I just want to show you what happens when I do that. So notice you can see the program every 1 second it's printing. It's not always printing spam in America or American spam. It's, again, unpredictable. But the idea is each of these is 1 second apart. And this can be useful for, I'm not familiar with Macs, unfortunately. But this can be useful if you want to tell a program to wait some duration. I can say that practically I don't use thread.sleep a lot, but it's at least worth knowing it exists. From there, what it does is it puts this thread that is currently running, so either T0 or T1, to sleep, and it will wake it up. That is, let the thread run again in this case, 1 second. If I want to do half a second, I can just change this to 500, because this measure is in milliseconds, or thousandths of a second. And so now you can see it's half a second apart. But that's the idea. So that's thread.sleep. Don't worry too much about the try-catch block yet. Are there any questions? Okay. So, quickly, again, you create a class that implements runnable. You create a run method. From there, you instantiate your runnable. You then pass that runnable to the thread, new thread runnable. This only takes in instances of classes that implement runnable. So this class, my runnable, has to implement runnable. And then you just start the thread. This will ultimately call the run function, but you never call the run function directly yourself when you're threading, because if you did call it directly yourself, it wouldn't run in parallel. It would run on the stack like any other function call. So we've shown these two. Just some things about the thread scheduler. This is the thing that chooses which threads run at this time. And this is the big takeaway. There's no guarantee about the order the threads are executed, and you can't control it easily. Effectively, you can't control it, and you have to, we'll get later to things like race conditions and locks, and how to avoid deadlock, etc. We'll get to that later today. But this is a big takeaway. You cannot control or predict the order. There is a way to stop threads. So we talked about how to run it. There is a way to stop threads, but you cannot use the stop method, which may seem obvious. What it is instead it's interrupt. And that is thread example 2. So if we take a look at thread example 2, let me minimize that. Take a look at thread example 2. You'll see I have this my runnable with interrupt. And the idea of my runnable with interrupt is that I'm going to ask, hey, have I been interrupted? If I have, I'm going to stop. Now, to be clear, an interrupt does not automatically stop a thread. An interrupt is a polite request to a thread to stop. It's saying to the thread, hey, if you could go ahead and just shut down, that would be great. But it's a request. It's an option. And so, when I create a thread, I can then start the thread. And if I perform, again, this is just time wasting. That's all I'm doing here is wasting time. I can then politely ask the thread to stop. But the thread can ignore me. Notice here it says the thread has not been interrupted. That is to say, I reached this if statement and the interrupt flag had not been thrown. Now, this if statement is something that you would typically put in a thread to check, hey, have I been interrupted? Has this thread been interrupted? If it has, this will return true. Thread interrupted. And so because I say not thread interrupted, if this statement is true, it means the thread has not been interrupted. So I say that, has not been interrupted. Otherwise, if it has been interrupted, I'm going to say I've been interrupted, and I'm going to return. To be clear, interrupts are a request. If you write your thread and you never have any kind of this if statement, you can completely ignore interrupts in your threads. You'll finish running. You don't care. This is a way to allow your thread to be interrupted. And the reason a user may want to interrupt the thread, if a process is taking too long, they might want to cancel it. It may be that you say you're doing that instant messenger application and it's downloading a message and then you lose internet connection. Rather than waiting for a message, you can have the thread interrupt, and so it will stop. But the idea is this is a way to have your thread interrupted. Now, you're not going to have to do this on the homework, but you will at least be expected to know about interrupts as it relates to the exam. So again, inside of a thread, inside of a run function, you can say if thread is interrupted. And if this is true, then you as the programmer, if the thread is interrupted, should find a way to exit gracefully and quickly. But notice I said the word should, not that you have to. Interrupting does not crash the thread. If I take out this return statement, the thread will finish. I don't have to return. It's just generally a good idea to do so. So if I take out this time waster, you'll see that now the thread has been interrupted, which means because I say return, it didn't proceed to this last print statement. Are there any questions? What is returned in the else statement? Nothing, because run must be void. Run cannot have a return type. Run cannot have a return type. So it's void. So I just return in a void function doesn't return anything. It just ends the function. Because a return statement always ends the function. So you can just call return like this in a void function to leave. It's like saying don't pass go, don't collect $200. Think of it like an emergency exit. It's like a break statement would be the most accurate thing to think of it as. Any questions so far? Here's the run. Here's the request to interrupt. That's all you have to do. Again, the developer of the thread should account for interrupts, especially if something is expected to take a long time. If something's going to take several seconds, you should account for this. You can use return to break from multiple nested loop. You just have to make sure you're doing it in a way that your function still works. But you can do that, yes. Like, if I'm implementing a find function, I'm just going to loop through whatever structure I've created, and if I find the element, I'm going to return the index. I don't finish the loop and then return. I just return. Because there it makes sense, but if I'm getting the sum, I can't return inside of the for loop. So, depends on the context. Usually you don't want to return in a for loop if you're getting summary data, but if you're trying to get like just one individual, then it might make sense to do so. Alright, so that's interrupts. And as a note, interrupts are a request to end. They are not a command. Sleep is used to suspend the execution of a thread. It does not stop it permanently. It just says wait some amount of time before you can run again. So a thread that is sleeping is not over. It is just basically waiting to wake up. So again, you have, like, for instance, if you have a large for loop, some large number of repetitions, it might make sense to do and not interrupted, so that way this for loop terminates if you are interrupted immediately. Might make sense to do that. You do have to have this try catch block whenever you do sleep. We'll talk more about try catch blocks later, but for now, just basically, this is all you have to do. Whatever the sleep is in, surround it with a try, which is similar to an if, a bit different. And then you need to catch, interrupted, exception, exception. You can copy and paste this part. And then if something happens with the interrupted exception, typically that means you need to just find a way to gracefully exit the thread. Terminate. Stop running. Again, Java does not force you to terminate. This is considered good practice, right? It's like the shopping cart. Nobody is going to yell at you if you don't return a shopping cart. At least nobody works for the store. I might yell at you because it's a dickish thing to do, but that's because I have anger issues. That is a joke. Kind of. Anyway. But nobody forces you to take the shopping cart and put it back into the cart thing in the parking lot. You're just supposed to do it because we live in a society. The same idea is true here. You're not forced to do it, but if a thread is likely to take a long amount of time, then you should do it. So now let's look at a practical example of threads, because these are two just little toy boxes that I've shown. For example, let's say that I want to look through a book and count the number of words. An example of this would be the book, or the collected works of Sherlock Holmes. This, give me 1 second, and I have uploaded, this is the entire open domain works involving Sherlock Holmes. Very specifically, it is not every Sherlock Holmes, because Sherlock Holmes is not entirely open source. If you haven't seen, there's a weird lawsuit going on right now where a company is being sued, but for giving Sherlock Holmes emotions. Because Sherlock Holmes' emotions are not public domain, even though the character is. It's weird. Anyway. That is actually a true story. But here is the collected works. It's a lot. This is 13,000 lines. So it's quite a bit. And the thing I want to do is I want to count, for example, in this thread, the number of times a given word appears. For example, I want to count how many times the word Sherlock appears, or the word Watson, or the word deduction. Now, I could do this by looping through the file 3 times. The first time I count the word Sherlock, second time Watson, third time I count the word deduction. Or I could just define a generic thread that reads through a file looking for words, which is what I do here. This takes in a file name for a text file and a string to look for. And then when I run, it's going to open that file. It's going to loop through one word at a time. And if it finds the word, it's going to increment the count. And then it's going to close. And then at the end, the last thing it does is print, I found that word, count number of times. And this is the thread. I define the file name in the constructor and the word I'm looking for in the constructor. The run actually takes care of looking for a word and a file. And the advantage of this is now I don't need to worry about the file or the word itself. I can just pass in the names here. And each thread will handle its own count. And as a result of this, I simply create an array of runnables. Here's my array. I initialize each with a different word. I create 3 threads, and I loop through the runnables, and for each runnable, I create a new thread and start it. And I could do this in such a way that I define as many threads as I want. I could have 100 threads looking for 100 different words here. And if I run this, you'll see that works. Deduction appears 10 times, Watson 81, Sherlock 97. Any questions about that? Again, this code is uploaded, so you can look at it, but I'll show the count again. Don't worry too much about how the file I/O is done. It just opens the file. This is a loop to go through the file one step at a time. If it finds the word, it increments count, and then ultimately it returns count. Any questions? Alright, so this is fairly straightforward. But now, all of these threads that I've done so far really function in a very specific way. What happens with these threads is that down here I have my main thread of execution. It's ongoing. And it creates, let's say, one thread, and then it creates another thread, and then it creates another. And these threads run, this one might be Sherlock, Watson, deduction. And these threads run, and eventually they print something, and that's it. They stop. They stop executing. And all these threads run independently of each other. They don't interact with each other. They're very self-contained, and that's fine. There's nothing wrong with that. But what if threads do need to interact? What if the main thread has some variable, and that variable needs to be modified? What if all of these threads share a single object? Now we can have a problem. And I'm going to illustrate that problem. I have a class here called bank account, and this is thread example 4 that I'm moving on to. And let's just first explain how bank account works. It's fairly straightforward enough. The bank account has a balance. When we create our bank account, it starts with a balance of 0. We can then deposit some amount. We can then withdraw some amount. And we can get the current balance. This is a fairly straightforward object. I want to make sure that everyone understands it, however. Are there any questions about bank account? Again, we have a balance, a constructor that initializes it to 0, deposit, which adds money, withdraw, that takes away money, and then get balance. There's no interest in this bank account, sorry. It's a checking account, more accurately. But does everyone understand this class? Because it's going to get confusing here in a second, but I just want to make sure everyone is aware that all I'm doing here is I'm defining a bank account with a single dollar amount, a deposit amount, a withdraw amount, and get balance. Now, I have 2 threads. 2 different types of, runnables, I should say, not threads. The first is a deposit runnable. This is going to take in a given bank account, a given amount of money to deposit, and a number of times to deposit that money. So, for example, if the amount were $100 and the count were 10, I would deposit $100 10 times. Ultimately 1,000, but the key is I'm doing multiple deposits. So all this is going to do is this is just going to deposit the amount. It's going to then wait 1 millisecond, and then it's going to deposit again, and then wait 1 millisecond, deposit again, until this loop is over, until count is done. So it's going to be fast. It's 1 millisecond. But the key is that we do actually have to put the thread to sleep. So again, deposit some amount, some count number of times. Similarly, I have another thread class. This is withdraw, and it's exactly the same as deposit, except instead of adding money, it is taking money away. So I withdraw an amount, count number of times. So this one calls the withdraw function. This one calls the deposit function. Any questions about those two threads? Or not threads, I should say, but runnable classes. We'll get to why I'm doing this in a second, but I just want to make sure people understand the bank account class and these two runnable classes. Any questions? All right. So now, I have this bank account thread runner class. And here's what it will do. It will create 100 threads. Actually, 200. But it will create 100 threads that are deposit threads. And 100 threads that are withdraw threads. And each of these threads is going to deposit or withdraw $100 100 times. So, add up the number of deposits and withdrawals we're doing. That's 100 times 100, which is 10,000, times 100, which is $1 million. So I'm depositing $1 million and I'm withdrawing $1 million. But I'm doing it 100 at a time. Given that I am doing it this way, I am creating the same number of deposits and withdraw threads. They are both operating the same number of times with the same amount of money. What should my balance be at the end of this program? Not rhetorical. If I deposit $1 million $100 at a time, and if I withdraw $1 million $100 at a time, what should ultimately be my balance at the end? 0, right? It should be 0. That is exactly correct. But it won't be. 1,100. Negative 200. 300. 1,400. Negative 300. Every time I run it, I'm getting a different number. And that's probably not a good sign, especially when none of those numbers were 0. So the question is, what is happening here? And the answer, it turns out, is a bit complicated. And it has to do with something called race conditions. You see, here's the thing about threads. I said it's unpredictable when they run. Well, they can also be paused automatically without calling thread.sleep. Java can pause a thread, and it can let another thread take its place. So someone asked before, what if we have too many threads? Java will just hot swap them in. I don't have 100 cores, but it is just randomly swapping them in, or again, randomly from my perspective. It's not random from Java's perspective. It has a reason. But it's not predictable to me. And here is what's happening. Let's just take the case of 2 deposit threads. See, the problem is, all of these threads are using the same bank account. And so there is one bank account variable which has one balance, and that balance is equal, right now, let's say the balance is 500. Let's say the balance is 500, and I am going to withdraw 100 with 2 different threads. The first thread over here, we'll call this thread 1, is going to call withdraw, and it is running the withdraw runnable code. So specifically, it's calling the withdraw function on account. So I'm going to put that code up. Here's the withdraw. Similarly, I have thread 2 also running withdraw, and they both have an amount. This one has an amount 100, this one has an amount 100. So they're both going to withdraw that. Now, here is what could happen. First, thread 1 says, okay, new balance equals balance 500 minus 100 equals 400. That would be the first line. That would be line 30. Right here, line 30. And then it executes line 31. Balance equals new balance, which means we come down here and we change this number from 500 to 400. Then the new thread, the second thread goes, it's going to withdraw 100, so it does new balance. Marker is, I ordered new markers today. They're coming. And unlike George R.R. Martin, I'm not lying when I say that. I am bitter. I'm a bitter, bitter man. So new balance equals 400 minus 100, 300. That's line 30. So line 31, balance equals new balance. Come down here, we change it to 300. Everything's fine, right? That's what it should be. This very well could happen, and typically this is what happens. But the following is also possible. What I'm about to show you also could happen. Again, we have our balance of 500. Two threads are withdrawing 100. The first thread starts running. Actually, let's do thread 2. Thread 2 starts running, and it says new balance equals balance minus the amount, 100. So it calculates new balance, and I'm just going to abbreviate it to NB. New balance equals 400. And then Java pauses this thread. It says, hang on, all right, you've had your turn. Now it's thread 1's turn. And so this thread is paused. It's no longer executing. Now thread 1 comes in, and it says, okay, I need to withdraw $100, so it's going to calculate new balance. Well, how does it do that? Calculates it the same way you see on line 30. New balance equals old balance minus 100 equals 400. Some of you may already see where this is going. And then thread 1 continues and it says, okay, well, the new balance is 400. I need to update the bank account's balance to be 400. And so it does. And then this thread is done. Yay, it's over. Now thread 2 picks back up. And it's finished line 30. It's already halfway done. So now it needs to advance to line 31, which again is balance equals new balance. So what does it do? It says, okay, balance equals new balance. So I need to change this bank account's balance to be 400. And now this thread is done. What's the problem here? We just withdrew $100 twice, and we only lost $100. Yay, free money, right? Do you think the bank's going to be happy about this one? No. The bank is not going to be happy about it. Maybe we, the customer, are, but keep in mind, we could do this in reverse. We could deposit $200 twice and only add $100. This is called race conditions. Race conditions. And race conditions occur when two threads are accessing a shared resource in such a way that once both threads perform an operation, the data integrity can be lost. It does not make sense that we start with a balance of 500, withdraw twice, and end up with 400. But this is the possible way to do it. Because Java and your computer could execute this instruction on line 30 and then could pause before it executes this. So now you may be thinking, okay, well, we can fix that. Let's just make this one line of code. The problem is it's two lines of code. Why don't we just say withdraw balance minus equals amount and balance minus equals or balance plus equals amount. I do see your question, Zealot. I'll get to it in a second. I just want to show that. This doesn't solve the problem. Because, and this is where it gets weird, this is not one line of code. And you may think, but yes it is. But remember, code is not necessarily what we the humans write. Remember, There's the Java file, which is the human readable code file, and then there's the class file, which actually has the machine instructions. This translates into 5 different machine instructions. It's not one line, it's 5. And each of those 5 instructions, you can be interrupted halfway through. So you can be interrupted in the middle of this line of code. And so the same race conditions can occur. Thus, when we run this program, even with this change, you'll see that I'm still not getting the correct value. 700, negative 400, negative 100. So what we need to do is we need to find a way to protect this value balance such that it is not subject to race conditions. And we'll do that in a second. So let me check here what I'm bad at Twitch names. Zealot says, does the print statement execute after all the threads are finished? No, so the print statement, yes, it executes after all the threads are finished. If we look about the thread runner, actually that's a good point. It doesn't. But I can make that happen. What I can do is I can say, I know how I did it. Give me 1 second. I know what I need to do. The original version of this was actually that after each transaction it printed. What I can do is update the withdraw runner that after it's done, it can do system.out.println account.balance or get balance. So at the end of every withdraw I print, that means I'm going to have 100 prints, but whatever. And I need to do the same with deposit runner. Let me copy that real quick. So this will make sure that it will print the balance after all the threads are done, because the last print statement will be when the last thread finishes. So let's run that. And there you can see I'm getting 1700, negative 4800, 3500, negative 2400. I mean, you can see sometimes it's changing, but yeah. It's still not 0. Yeah, it actually is worse. So that was a good point, Zealot, though. I had actually made changes to this during the lecture in the spring, and I forgot to undo those. So thank you for pointing that out. So now, the motivation for the second half of class is going to be, we need to solve race conditions. We need to not allow that to happen. Now, I want to be clear what is going on here, because this is where it gets a bit complicated. You know, we talked about the heap and the stack, right? Well, as this relates to threads, every thread has their own stack, but every thread shares the same heap. So if you think of this like stack and heap, as we've done before, here's my heap. This is stack, and I'll call this T0 for the first stack, for the first thread, and stack T1, and stack T2. And all of these are inside some run function, except for the main thread. The main thread is going to be inside of main at the bottom, because this is what Java runs when you first start. So what is happening here is the bank account, remember, objects are stored on the heap. So my bank account, wow, this marker's really dying. Hopefully my box of markers is outside. I'll check in the break, because the green just does not show up well on camera. So I have some bank account, and this has an integer balance, which is equal to some number. What is happening is, because I'm creating every thread, I'm passing into the constructor the same bank account. That has a variable called account, which you can see here, right there. That is account. And each of these threads, again, not counting the main thread, I'm talking about the ones I create as runnables run, has an account. that points to this same account. So these are the reference. So I just want to be clear how the stack heap works. The idea is all threads share the same heap. All of them. But each thread has a different stack. So the local variables are all different. But the instance variables stored on the heap, those are all shared. So I just want that to be aware of that. So we will solve race conditions after the break. We're going to take a brief break. I'm going to see if my markers are here. Fingers crossed. And I will see everyone on the other side. I'm going to leave the code up. But again, take a look, download, make sure you can get them up. Thread example 1, 2, 3, and 4. You'll need different Java projects for each. And then we'll look at 5 and 6. Again, just a note. Thread examples 4, it has the word bad in parentheses on it. That's because this is what I have here. It's the race conditions that don't work. And that's intended to show you what can go wrong. Thread example 5, which we'll pick up after the break, is how we fix it. So I'll see everyone then. Be right back. Obviously not 2:24. What time is it now? We'll make this 2:12. So go ahead, go get yourself a cup of coffee or whatever you do. Me, it's this, and we'll be back. All right, we're back, everyone. Pardon me. My cats are swarming. They want attention. They're Scooby Doo. I was giving them a little dance number or anything. But with that, we are ready to jump back in. So we left off talking about race conditions. The idea that two threads try to access the same variable at roughly the same time, and as a result, they both get in each other's way, and they break the variable. They ruin the data integrity. So now we're going to talk about how to fix that problem. And in order to do that, we first need to talk a little bit about locks. So let me make sure I have the right. Here we go. Race conditions and synchronization. So again, the problem, and we showed this already, is that we can basically have two threads try to access the variable at close to the same time, and as a result, so here we have the balance is 0, two deposit threads run, and now we have a balance of $100, even though it should be 200. And it's because they both start with the wrong value. And so, or they both start with the same value, and they both only add 100 and then set it to that. So, the end result should be 0 if we're withdrawing and depositing enough times, but we never got 0 the multiple times we ran. And this occurs whenever, or this can occur, I should say, race conditions can occur whenever multiple threads try to access the same data at the same time. And so, because of this, the race condition can occur not just here, but really on the right-hand side as well. So what we need instead is to do a lock. A lock is going to limit how many threads can access a given variable at a given time or call a given function at a given time, such that only one function is operating in a, and this is, we're using this term differently than when we did with algorithms, within a critical section. That is, in a situation where a variable can change as a result of the run, we are making sure that only one function can be in there at a time. Best metaphor I can give for this is imagine a very busy nightclub. It's incredibly crowded, and everyone needs to go to the bathroom, but there's only one bathroom. Now, rather than form an orderly line, everyone's just crammed against the door trying to get in, and someone will get in, but once they're in, they're the only one who can be there. Everyone else has to wait. And that is a weird metaphor, yes. But someone told me that once, and it stuck with me. I didn't go to nightclubs because you could probably tell I'm not that kind of person. But that is still something that stuck with me over the years. And so the first thing we need to do is we need to create and initialize a re-entrant lock. So let's do that. We're going to create a private, and then I want to draw attention to the fact that this lock is attached not to the runnable, but to the resource. So you don't put the lock in the thread, you put the lock in the thing that needs to be protected, specifically the bank account. So it's very important where you put the lock. So private lock, and what did I call it in the slides? I called it balance change lock. Private lock, balance change lock. And you do need to import a library for this. The library that we're importing is java.util.concurrent.locks. So you can see it here. From there, in our constructor, we need to initialize that lock. Lock equals, or excuse me, balance change lock equals new re-entrant lock. And we have to import that as well. So we initialize the lock, and this is only protecting this bank account. So if I made 10 bank accounts, I would have 10 locks, each one with their own lock. So it's not one lock for every bank account. It's not static. It's one lock for each bank account. It's non-static. From there, the way this lock works is Oh, sorry, I put this in the wrong place, didn't I? I kept saying this needs to be with the bank account, and I thought I had bank account open and I didn't. Apologies. Let me do bank account here. I'm going to create that lock. You don't put the lock inside the thread. Apologies there. I even said that, but I just didn't notice which file I was editing. Let me close all. And then we initialize the lock in the constructor. And from there, whenever we do a deposit, we are going to say balance change lock dot lock. And this is like walk into the bathroom and lock the door behind you. And then, once you're done doing whatever you need to do, then you do balance change dot unlock, or balance change lock dot unlock. And this releases the lock, effectively leaving the bathroom unlocked for the next person to come in. And we want to do that anytime we manipulate the value of balance. Anytime we change the value of the shared resource, we want to protect it. So, I also lock and unlock when I withdraw. I do not, however, need to lock or unlock when I get balance. Why don't I need to lock here? Can anyone tell me why I don't need a lock here? Why don't I need a lock on get balance? I'm not changing its value, correct. I'm not changing it. And so the worst case scenario is I get a value that's out of date, but it doesn't let me edit that value. So you only need to protect technically edits. And now, when I do this, and nothing up either sleeve, I'm not wearing sleeves. All I did, I added a lock, I initialize it in the constructor, I lock and unlock before I deposit, or I lock before I deposit and unlock after I'm done. I lock before I withdraw and unlock after I'm done. And now you'll see that my ending balance is 0. Now you can see it change. You can see each thread change the value as it ends. But ultimately, no matter how many times I run this, the value ultimately ends in 0. That's because I can never have race conditions again. What will happen is, going back to this diagram that we had up a second ago, this can never occur because it would involve two separate threads performing this locked, protected operation at the same time. So thread 1 would have to finish completely before thread 2 could proceed. That's the key. Now, are there any questions about this before I do the next step? Any questions about what I'm doing here? Why does it remain the same number multiple times in a row? It's because of where. So that's a good question. It's because of where I'm printing. If you notice, I'm printing when the thread ends, and that's after the loop is over. So it could be that a bunch of threads finish but don't print, and then all at once they all print one bang 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 after they're all done. So that's why they're printing the same value. It also could be the value shifts by more than 100 because I'm not printing on every deposit. I could change it to do that. You'd see every value change by 100 at a time. It would just be a lot more print statements. So I'm only printing the end value. How do you initialize the lock? Just to show that again. So I define a lock variable as belonging to the class. And from there, I initialize the lock when I create the bank account. This is like putting a door with a lock on it. It does not lock the door. The door is initially unlocked. But it says, hey, this is a door with a lock on it. And we're putting balance behind that door. So new reentrant lock. So a lock data type, lock is abstract, reentrant lock is concrete. Do we have to do this for every class when we go into industry? Well, that's a broad question. This is not the only way to do threading in Java even. So there's something like the synchronized keyword, although the reason I'm showing you this is it supports more features. The idea of threading and the idea of race conditions appears in basically every modern programming language. And all languages have to worry about race conditions. So this is how Java handles it. So for the sake of this class and you know, other classes that you'll take that use Java heavily further down the line, this is how you would handle it. But you know, if you're in Python, how you handle threads obviously isn't this way, but you have to handle them in some similar way. This, more generally, is often called, there's a word for this that you'll hear later on. It's called a semaphore, if you've ever heard this term. And pretty much all modern languages have some form of semaphore. So now, there is a disadvantage to this. Now, we get data integrity. And data integrity is the most important thing. So this is what I'm about to say is not something where we're like, oh, what's the trade-off? The trade-off is if we don't do this, we lose data integrity. And that's bad, really bad. But we lose performance by doing this. Because keep in mind, before, in theory, we could have 100 threads performing this operation at the same time. Now how many threads can perform this operation? Only one. This is a bottleneck. By that I mean, think of this block section like all the threads are running. Look how much bigger this is. I got so many dry erase markers. All the threads could be running, and this lock is like a bottleneck. And it's a bottleneck that only one thread can go through at a time. And this is where the critical section of changing the value of balance is. And then at that point, they can all run again. But what happens is all the threads get stacked up and only one can pass through this area at a time. It slows down all of the threads' completion. Now, the thing the threads do that are not in this bottleneck are not slowed down at all. It's only slowed down once they're waiting to enter this bottleneck. But only one thread can go at a time. The reality is, as much as it sucks to have to do this, as much as it sucks to lose that performance, this is the only way to solve the data integrity problem. The only way to do it. So we do lose some performance in order to secure data integrity, but that's because data integrity is not an option. Our data has to be correct. Any questions about that, or what I mean by a bottleneck? A bottleneck is like the Battle of Thermopylae, or if you prefer, the movie 300. It's a narrow space that only a small number of things can pass through at one time. Bottlenecks typically slow down the process, is the idea. It takes longer to move an army through a bottleneck than wide open terrain. So now, I'm going to add to this a bit, and I'm just going to show you the version that's uploaded, and I want to explain why it's written the way it is, because it maybe looks a bit confusing. Something that can happen from time to time is that your code crashes unexpectedly. This could be for any number of reasons. Could be because someone terminates the program abruptly. Maybe some other part of the program crashes. In either case, you need to be prepared for your code to crash, even in places where it doesn't make sense. And one thing you have to worry about is, what if I somehow crash in here? What if you pulled an Elvis Presley? If you don't know, Elvis Presley died in a bathroom. And thus, you go in the bathroom, you lock the door, and then you die. And you can never unlock the door because you're dead now. That's an Elvis Presley. And yes, I have used that metaphor before while talking about threads. In that situation, now you have a ton of threads that are stuck outside waiting to get in. One thread that's just dead in here, and so none of the threads can cleanly terminate. So here is what you need to do. You need to do this. This, by the way, is a more full version that prints each deposit. You can see that here. You lock the door, so you go into the bathroom, you lock the door, you do your balance operation, and then rather than unlock, what you'd have is a try block. And the way this works is if for whatever reason I crash inside of this block, the code will execute whatever is in the finally block. It doesn't matter why I crash. It will execute the finally block. And so, this, think of this like if the fire alarm goes off and you have to leave, you leave, but you leave the bathroom door unlocked behind you. So, if there's any chance of code crashing, you have to wrap the thing that after the lock in a try statement. Then if this crashes or not, this finally block runs whether you crash or not. If you finish the code without any problems, you still run finally. If you crash inside of here, you still run finally. The point is, no matter what happens, you will unlock. So this is actually what you should do. But now I have a problem. And this is, by the way, to illustrate down here. You can have multiple locks. So I have so I added, this was just a question the student asked, and I left this in because I think it's a good example. If I have a separate variable, in this case x, and I have functions that are very similar to deposit withdraw, just incx and decrement x, you still need to protect that, but I can protect it with a separate lock. Because x is a separate resource from balance, and I don't have to worry about the two conflicting with each other, changing x is not going to affect balance, I can create two separate locks. So you have one room, or bathroom, as I've been using the metaphor awkwardly. One room serves for changing the balance, and one room serves for changing x. And these two rooms are separate. They don't need to interact with each other. So if you'll notice, I have two separate locks. Here I don't do the try finally, but just illustrating this again. Okay. So this is an example just of the bank account. I'll show the bank account thread runner. You can see that in this case, I added to the deposit runnable that it, well, it's still just depositing. It also increments X. And the withdraws and decrements X. And that's just to show that these two locks work in parallel. And the advantage of this is now we don't have one bottleneck. We have two. And you may think that's worse, right? Two bottlenecks is worse than one. But these bottlenecks, because they use different locks, they're kind of in parallel. And so a thread can be in both of these. You can have one thread in one bottleneck and one thread in another. So you can still have two things running at the same time because these are different locks. This is my balance lock. And this is my X lock. So I uploaded that finished version from the spring just because people were wondering about, do you use one lock for multiple variables or do you use one lock for each variable? If the variables can be changed independently, like X and balance can, then you can have two separate locks. If the variables are codependent, by which I mean changing one variable necessitates changing another, then you need one lock for both variables. But in this case, the way I did X and account, or the count and the amount variables, they are, excuse me. The way I did this X and this balance variable, they are separate. They never interact with each other. But now let's take a look at this bank account and let's notice a couple things here. So I'm going to run this bank account thread runner. And you'll notice that At some points, I have a balance that is negative. New balance is negative. Here's a bunch that are negative. And banks do not like you to overdraft. They will penalize you if you ever do this. Even if you deposit later, you have to pay a penalty. And so, in addition to allowing people to deposit whenever they or however they want, we need to account for in bank account the fact that you can only withdraw if you have sufficient funds to handle that. So we need to add another layer of protection such that we never withdraw ourselves into the negative. That if someone tries to withdraw money when the funds are not available, they are told to wait until funds are available. So how can we do that? And that takes us to the part 3. And that part 3 is, it's called avoiding deadlock, but this is going to have to do with what we're going to refer to as conditions. Not conditionals, not if statements, although they'll be used, but conditions. So, a deadlock occurs if no thread can proceed because each thread is waiting for another to do some work first. And something that can happen here is that when I am trying to withdraw, I am waiting for the balance to change. And if I do this, I could run into problems. Namely, if I were to just plug in to my withdraw function something like, after I lock, while balance is less than amount. That is to say, I have insufficient funds. Maybe I do something like threads.sleep. Wait 1 second, right? But I can't do this because the problem is this. Where am I waiting? I'm waiting inside the lock. This thread has the lock in hand, and it will not let it go until the function ends. So I would be trapped in this loop infinitely because because the balance would never change. I have the balance lock. I have the key to this lock. No one else can have it. So what I need to do, and I'm going to diagram this out, is the following. Where'd my eraser go? There it is. What I need to do is the following. The variable balance is behind a door. You're going to see my amazing art skills here. Behind a door with a little lock on it. And there is a key. I am bad at drawing keys. Try. There we go. Tried to draw an artistic key and it didn't work out very well. Okay, this is the key. Look at my amazing art skill. This is a key to that lock. So I'm going to call this my balance key. The idea is a thread grabs this key, uses it to walk inside, and while the thread is in here, hang on, I have a fruit fly flying around here. It is holding on to this key. No one else can have this key because it is in this thread's hand behind the locked door. But what will happen is the thread gets in here and it says, oh crap, I can't withdraw funds. I can't withdraw funds because there aren't enough funds. So what's it going to do? Is it just going to sit behind this locked door waiting for someone to deposit? Well, it can't because, the balance variable is behind this locked door and there's only one key. Balance variable can't get to it. So what has to happen is it has to temporarily give the key up. It has to temporarily give the key up. It doesn't need to leave the room, but the rule is it can't proceed until it has the key again. So it needs to give this key up on the condition that it will eventually get the key back. And that's the idea. We're going to have the withdraw thread temporarily give up control of the lock on a condition that it will get it back again. This is why I really shouldn't try to draw anything in class, because that did not turn out well at all. So now, how do we do that? Well, the first step is we are going to create something called a condition. And that condition is an object that is attached to a lock. This condition belongs to a specific lock object. And this condition will allow a thread to temporarily give up a key, but regain it at a later time when it can proceed. So you can think of the withdraw thread as giving up the key until enough deposits have been made that it can withdraw its own funds. And so, in addition to creating our lock, we're going to create a condition that is attached to that lock. So to illustrate this in the code, we're going to just add to what we have. I'm going to define a private condition sufficient funds condition. Oh, I misspelled that. I'm going to define a condition, which is also in java.util.concurrentlocks. And then, at the time that I create my lock, I'm also going to create my condition attached to it. Sufficient fund condition equals new or equals balance change lock dot new condition. This is how the condition gets tied to that lock. And a condition can only be tied to one lock. I can't have one condition that interacts with two separate locks. Then from there, the withdraw function, it's still going to check, it's going to wait while balance is less than amount. But when I wait, in order to temporarily give up the lock, I am going to say sufficient fund condition dot await. And you do need a try catch block here. So, actually, you just need to add a catch statement. So I'm just going to add the catch clause interrupted exception. But you don't really have to worry about what this does. It needs to be there. Java won't compile without it. We'll talk later next week about how this exactly works and checked versus unchecked exceptions and everything. For now, you can just put that there. So we're going to tell this condition await. And what this means is this pauses the thread and it waits for a signal. That is, this thread will not attempt to proceed until someone tells you, hey, the coast is clear, you can try now. We'll talk about how we do that in a second. So this is the idea. We're going to have our waiting condition. If this is true, we're going to wait. You'll notice I used a while loop instead of an if statement. This is because it's possible that when the thread is woken up, there still isn't enough balance to cover the withdrawal, and so it has to wait again. So what will happen is, if the balance is less than the amount, it will pause itself and wait for a signal. When the thread is woken up, it will immediately proceed from this line of code, but it's still in a while loop, so it loops back up and checks the condition. If this is still true, it will wait again. But eventually this will not be true anymore. At that point, we'll have enough balance to cover the withdrawal amount, and we will perform the withdrawal. And then we unlock. So notice we don't unlock here. We're temporarily giving up the lock. But the thread will proceed again once it has been signaled that it's okay to proceed. So that's the first part. That is telling the withdraw thread to await. The second step then is to signal all. That is to say, this is, hey, the coast is clear. All the awaiting threads awaiting this condition, you can proceed now. If we're waiting to withdraw funds, and we're waiting until we have a sufficient balance, what would be the best time to say, hey, all you withdraw threads that are waiting, you can try again now? When would we want to do that? When would we want to let all the threads know, hey, go ahead, give it a shot? If we're waiting to withdraw funds. What's the best time to say, hey, wake up, try again? Every second? No, that wouldn't make sense. After a deposit, exactly. After we add money. After we add money, we can simply say, okay, all you threads that are waiting on the sufficient fund condition, give it a shot. Wakes up awaiting threads. Now, here's the key about this condition. Because this condition is tied to this lock, or excuse me, the balance change lock, because this condition is tied to this lock, we can only call signal all or await. We're only allowed to call these in between calling balance change lock and unlock. We have to have the lock to interact with the condition. If you put this outside of a lock, your program will crash. And it will give you a weird error message. So, now let's try this. Let's see if we ever get below 0 now. Okay, the program finished. Let's scroll up. Let's see if we see any negative numbers. We don't. We do hit 0 sometimes. Like here we got close, didn't hit 0 there. Where is 0? Let me see if I can find a 0. Kind of looking for a needle in a haystack here. There's some low numbers. No, not a 0, though. Here we go, some 100s. There's a 0. But we never go negative. We never go negative. And it's because if the withdraw amount were less than the balance, we tell this thread to wait until there's enough money to withdraw. So that is our safety condition. We're saying, okay, you can't proceed yet, but we'll let you know when you can proceed. We'll let you know by calling signal all. Now, I want to be clear. If you don't call signal all, this thread will stay asleep forever. It would be like Sleeping Beauty, only there actually wouldn't be an ending. She would just go to sleep and that would be the end. It would be a lot more tragic, although let's be honest, it's kind of a creepy story regardless. So if I comment this out, those threads will never get woken up. And to show you what happens, this happens. You see how I still have this red stop sign? That's because my program is still running. Because there are threads that never finished. There are threads that are stuck in this while loop, waiting, begging for me to wake them up so they can end their misery. But no, they're stuck running in circles. Like, what's his name? Sisyphus. Like Sisyphus pushing a boulder up a hill. That's what these threads are stuck doing. So, don't torture your threads, folks. Make sure that you call signal all to wake them up. Your threads don't want to be Sisyphus. They're more like Meeseeks, really. You're actually, if you've seen Rick and Morty, threads are Meeseeks. Done. And if you have no idea what I'm talking about, I'm sorry. It's actually a great show. Threads are Meeseeks. Anyway, so what I just showed, that is with the conditions and everything, that is here inside of thread example 6 as uploaded. So you didn't have to necessarily follow along with every line of code I wrote there. The solution, I'll just close everything and show you, The solution is already here in, thread example 6, which is uploaded. You can see here's where I do the signal all. Here is where I do the await. Any questions about this? Because here's the fun part. We're going to do the daily activity, and I'm going to let everyone get started on it. I'll let you work on it with each other for like 8-10 minutes, and then I'm going to do it with you. Because this is a harder daily activity, but it also translates very, very tightly with the homework. And so if you follow along with me and make sure you understand everything as we go, then I will be very happy to point back to this when you're doing the homework and say, see, this really helped. So, go ahead and get started with today's daily activity. Get started with each other. Jump into Discord. Right now, there's only one person there, so everyone jump in and help each other out. See if you can do the daily activity, and then we'll come back and we'll do it together here in 10 minutes. But it is up on Colab. And I will at least start installing it as well. So I'm going to make my own new project. 0702 daily activity. I'm not sure what you mean by the root folder for the files. So the files, if you notice on thread example 3, the files go in the root directory, so that is the project directory. So Sherlock.txt is inside of thread example. It is not inside of source. So all your Java files have to be inside of source, but your text files need to just be in the package. So I'll actually show that process here. So here I've created a folder for my daily activity. I'm going to go to Colab. Although I have to make sure that there's nothing on the screen that violates anyone's privacy first. Okay. And then I'm going to go to assignments. I'm going to go to daily activity for today. I'm going to download all of these files. So you can just do right click, save link as. And you can see I've actually already saved them. From there, I'm going to go to those files. And I am going to, give me 1 second here. I'm just going to click and drag them into the folder. Specifically, the code goes into the source folder. And the books go just into the project folder itself, not source. And there we go. And from there, your goal, as described, is as follows. You want to create a thread that runs all over each of these files. And the goal, ultimately, is to count how many words are in each file. So, in.next gets the next token, you just count, etc. Let me pull up the instructions again just to make sure everyone understands. So, you're going to modify the word count runnable to include 2 static fields, thread count and combined word count. So I don't just want, I want to be clear on this, I don't just want each thread to have its own count. I want there to be in the threads, I want there to be a static field, static int thread count. This is going to keep track of my number of threads or number of runnable instances. And we can make that, I didn't say in the assignment, so you're welcome to make this public if you want. And public static int Combined word count. Total number of words. And the instructions are here. And we'll work through it together, but see if you can do it yourselves before we do. And I'll give you 10 minutes from now, and then at 3:02 p.m., I will pick this back up and I will show you my solution. We'll be back. All right, we are back. Hello, everyone. So let's see how the bald guy would do it. So let's make sure that we're following along with the directions. The first thing it said to do, modify the word count runnable class to include two static int fields, thread count and combined word count. Now I want to clarify why these fields are static as opposed to being non-static. The idea is this is a class of runnables. That is to say, this is a class that describes a way to make a thread. And we can have multiple instances. So I could have, say, 5 threads, or 10 threads, or 100 threads. The point is, I can have as many threads as I want. But I only want one combined word count. That is the word count of all the threads I make combined. And I only want one thread count, which is going to be how many times have I instantiated this class. How many times have I instantiated? So because this describes the class, they need to be static. So I am going to, every time I create a thread, every time I create, or I should say anytime I create a runnable, I am then going to say thread count plus plus, right? Because I'm creating the runnable to create a thread, and so I do thread count plus plus. Are there any questions about this? Because I'm going to go very slow on this because there's a lot of moving parts, and I want to make sure that everyone gets each piece as I build it. So every time I create a runnable, I'm going to say thread count plus plus. And remember, this doesn't mean that every thread has a count of 1. It means the first thread, the first time I call the constructor, this becomes 1. The second time I call it, this will become 2. The third time I call it, this will become 3. Because it's static, so it belongs to the class, not to any one instance. So we talked about static before, but I know it is something that's a bit tricky to get the first couple of times. So hopefully this is a good example to help explain it. Now, from there, if I increment thread count when I create a thread, I need to decrement thread count when the last thread completes. So, or excuse me, not when the last thread completes. Every time a thread completes, I need to decrement thread count. Thread count minus minus. This is because I create the thread when I call the constructor, and the thread is over when I finish the run function. So if I create 10 threads, I'm going to increment each time in the constructor once, and I'm going to decrement each time run finishes once. So my number, which is initially 0, will rise when I create a new thread and run, or and fall whenever I finish running a thread. Does that make sense? Please ask. I will very happily answer a question if you're confused as to why I'm doing this. I just want to make sure everyone understands this part before I make it harder. Okay. So now, there's a problem. Because this run function happens in parallel, right? This is multi-threaded. And that means that now I have a shared resource, shared because this is shared among every thread. Do the word static. This is a shared resource. And because this resource is shared, in order for thread minus minus to be accurate, I need to protect it with a lock. So I need to create a lock. I think I just have this indented wrong. Let me fix the indentations. There we go. I need to create a lock, private static lock, thread count lock equals new reentrant lock. And I need to import these two libraries like we did before. Now, I am making this static because it is protecting a static resource. I did not make the bank account balance lock static because the bank account balance was non-static. So if you're protecting a static resource, the lock must also be static. That is, there is one lock that all of the instances of this class share, as opposed to each instance having its own lock. And all I need to do when I modify thread count is I need to say, first, thread count lock dot lock. And then, once I am done, thread count lock unlock. And I should, for the sake of thread safety, do the same when I instantiate. So, thread count lock, thread count unlock. I don't need to protect file name, because file name belongs to each individual thread. Only one thread will be accessing this file name at a time, and it's the thread who owns that file name. So I don't need to protect that. But does anyone understand what I did with thread count, or anyone not understand, I should say, what I did with thread count, why I made it static, why I made a static lock, why I lock before I increment here, and unlock before or lock before I decrement here? Are there any questions about any of that, or does everyone understand this? Because I will tell you, this is pretty much exactly what you're doing on the homework. But the difference is you're going to have to do that one on your own. Alright, so now we've done why lock is put in runnable this time. Because the resource I am locking is in this class. So the shared resource I am locking is the shared variable thread count. Because thread count is static, it means that it is not belonging to any one runnable. It is shared by every instance of this class. So you need to lock shared resources. And static effectively means shared. So you lock resources that could be subject to multiple threads trying to access them at the same time. Because this is static, multiple threads may try to access it at one time. And so we have to put it in the lock. The last time the shared resource was the balance inside the account object. That's why we locked that. This time the shared resource is the static thread count in word count runnable. So any shared resource is what we need to protect. Because remember, there is no this.thread count. There is the class.thread count. And that is a difference. That is a distinction. Alright. So now, we have that. But we also want to get the combined word count. So let's read the directions, see what it wants us to do. We've done step 4. Now let's do step 5. Use the combined word count to keep up with the total words of all files. So that means I want the total number of words. Now, how do I get the number of words from an individual file? Well, I get count. And so what I'm going to do is, after this loop is over, after I'm done looping through the file, I'm going to take this value count and I'm going to increase combined word count by this amount. Notice that count is a local variable, so each thread has its own count, but each thread shares the same combined word count. So once this is done, I can simply say, after I close the file, count, or combined word count plus equals count. Right? Does this make sense? Why I would do this? Again, I'm trying to get for every thread, what is the total word count? So for each thread, take its local count and add it to the combined word count. Does everyone understand this? Remember that this is a static variable on the left. This is a local variable on the right. Now, what's a problem? If this is a shared resource, and it is, if this is a shared resource, what do I need to do? I need to protect this resource, right? So I need a lock, exactly. So, if you like it, then you should have put a lock on it. No, don't. No, that was bad. Everyone boo me. Boo this man. Boo him. I'm just going to call this combined word lock. Equals new re-entrant lock. And then, before I increment, combined word lock dot lock and combined word lock unlock. Now, I want to be very clear. I, as a programmer, me as a human being, decided that this lock applies to this variable and this lock applies to this variable. Understand that that is a human decision that I made, and that is why I wrote the code the way I did. But that is not something that Java did. Java has no idea whatsoever that this lock is attached to this variable. Java doesn't care. I could lock this lock whenever I want. I could unlock it whenever I want. It is my job as a human to use this lock to protect this variable. So I want to be clear, there's nothing programmatically attaching these two things other than how I use it. So now, I am adding the combined word count, but it is protected. Let's look at the rest of the directions. When the last thread finishes, print out the total number of words. Well, here's my question. Given my code, how will I know when the last thread finishes? How will I know when the last thread finishes? Does anyone have an idea? Exactly, when the thread count equals 0. So, if, and I will want to, in this case, I actually will want to do this inside of the lock, because I only want to do this once. So I only want the thread that makes thread count equal to 0 do this. So, if thread count equals 0, then I'm going to print combined word count. System.out.println combined word count. And I'm doing this inside of the lock because I only want the thread that makes it 0 do it. Otherwise, if I do it outside, it's not going to result in any data integrity, but it's possible I would have two threads finish near the same time and both would print this, so I would get it twice. Since I only want it to happen once, I put it inside of the lock. And I'll even write the word combined count equals, just so that way when it prints, it's clear what happens. And then from there, just acknowledging, so it said use the locks to ensure. That's fine. That's what I did. And here is my solution. So let's run it. Let's do the word count.java test. And let's see if we get the same result every time. That is to say that this is secure. Here we go. Run, and notice that each of them prints the count. The last one prints the total, which is correctly the sum of all of these numbers. And it only prints combined count one time. Now, if I run this multiple times, Macbeth is actually shorter than Hamlet. The reason I'm typically going to get these in the same order just because the files are very different length, but it's possible they could appear in a different order. The point is only the last thread shows combined count. So let me show you that solution again. And if you want to copy it, I have no problem with that. I'm going to start with the top half. Here's the top half. And again, you can always clip this and come back to it. Wink, wink, nudge, nudge, hint, hint, elbow, elbow. Right? You can always clip what I'm about to do and then come back to it and look at it later. So here is the top part. Here's my thread count lock and my thread count. Here is my combined word lock and my combined word count. Here is where I increment thread when I create the runnable. Here is where I decrement thread when I end the runnable. And check, is this the last thread? And if it is, I do that. Here's where I increment the count. And notice I lock it. Now, wink, wink, hint, hint, nudge, nudge, clip. Anyway, the next thing I want to point out is this. What if I did the following? This is a question I am asking each of you. What if I do this? What I have done is I have moved the locks up considerably. Will this still work? That's my first question. Yes or no? Pick a side. We're at war. You can't sit on the fence. I know I'm out of time. I apologize. Yes, this will work. But it will be slower. This will work. The key is, though, you don't want to do this because this makes the bottleneck longer. Now the bottleneck is this entire code. This is all in the bottleneck, and that's bad. We want bottlenecks to be short. We want the bottleneck to get in and get out. You don't want someone in the bathroom for 30 minutes. You want them in there for as short a time as possible. And so, can you lock and unlock at the start of the method? Yes. But you should only do so at the end. And I do apologize for running over, but I was just solving the daily activity for you. So, I technically didn't present new material. Anyway, I am going to wrap up lecture here. I do apologize, mea culpas, for running over. But I did want you to see this, because seeing this will very, 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 very much help you with the second part of homework 4. With that, have an amazing weekend, everyone. I'm sure I will see some of you in office hours. And take care. I'll also stick around for a second and answer any chat questions. But the lecture part is over. So here, look, we'll do the whole, ending screen. And the music, cue music. All right, music was cued. I'll answer a couple last questions here. There is unfortunately not, to my knowledge, a traditional European folk dance to help you understand multi-threading. I apologize. If someone finds it, please share. I would greatly appreciate it. Will I be teaching 3240 in the spring? I don't know what I'm teaching in the spring. No one knows what anyone is teaching in the spring. So typically by now the schedule would be set. But as you know, the world is, let's call it, abnormal right now. Now, one thing I do want to prepare you for is if you take 2150 in the fall, there is a good to fair chance, I would say a very likely chance, that you won't get into 3240 in the spring. And the simple reason is it is a very crowded class. It is a class that a lot of people want to take. And so, yeah. Is Quiz 6 on recursion and concurrency? It's on both, yes. There should be no info from next week. Mentioned that you're going to remove a question from other quizzes. Is that happening? Yes, I just haven't done it yet. I'll post a Piazza announcement when I do. I haven't had the time. I apologize. I have actually been working on this class really hard. Producing all these materials and everything. So I do apologize. It will get done over the weekend. I just don't know when. Is there a solution available to the daily assignment from yesterday available? Post that question on Piazza, and I'll respond on Piazza with a solution. Or one of my TAs will. So if you ever want a solution to a daily activity after the day, I won't post it the day of. Just ask on Piazza, and that's the easiest way for me to do it. Otherwise, have a great weekend, everyone. Alright, I am going for real this time because I want to eat some food before I do that. If my computer is still running the word count class, is it likely being slow? It could be because it's slow, or it could be because you deadlocked. Do you ever unlock? This is my question. Because if you never unlock, it could be that your program has frozen. Is there office hours tomorrow? Yes. The bald man will have office hours tomorrow. Yeah, I will be there at whatever time I say on my schedule page on Discord. I just do as Google Calendar commands. I have no foreknowledge of the future. But I do have office hours tomorrow, and I do plan to hold them. I might have to take a break from, yeah. Alright. I have office hours in 7 minutes, and I'm, like, really hungry for lunch. So I'm gonna go do that. And otherwise, have a great weekend, everyone. Take care.